Welcome everybody. We're going to start this webinar on dose individualization using the example of Tobramycin. My name is Geraldine Herald. I'm the VP application at Lixoft. So this webinar will be recorded, so if you want to go back to it afterwards, you will be able to listen to it again. The presentation will last 45 minutes. During this time, please mute your mic so that we avoid background noise. And we will have 15 minutes at the end for questions. So dose individualization has been shown to improve patient outcomes and reduce adverse events. I have listed here two publications that show the benefits of dose individualization, but there are many more. Now the question is how to do dose individualization in practice. And this is what I will show you today using the example of Tobramycin. Tobramycin is an antimicrobial agent from the aminoglycoside family. It is, for instance, used against severe gram-negative infections. And what is interesting about this molecule is that it has a narrow therapeutic window. For efficacy, the peak concentration must be within 6 to 7 milligrams per liter, but to avoid the risk of nephrotoxicity and ototoxicity, the trough concentration must be below 2 milligrams per liter. And because it is not so easy to reach this narrow therapeutic window, what we would like to do is to develop a population PK model and to use this model to determine a priori the best dosing regimen for specific patients via simulations. So the workflow will be the following. We will first have a look at the clinical data set that I have used to build the model. We will visualize this data using DATExplore to get a bit more familiar with it. We will then move on to Monolix to develop a model to characterize the pharmacokinetics of Tobramycin. And finally, we will use this model for optimal dose finding for specific individuals using Simulix. So let's first have a look at the data. Here I have opened the data in Excel so that you can see how it looks like. It has a very typical format. We have a column ID with the ID of the patients, a column time, a column EVID. So if I have a 1 in this column, it means that the line is a dose line and the dose is recorded in the dose column. And if I have a 0, it means that it is a response line and the measured Tobramycin concentration is recorded in the CP column. So as you can see, we have a lot of doses and sparse measurements. And in addition, I have for covariates, weight, age, sex, and creatinine clearance. So here we have in total 97 individuals. We repeated bolus doses. The data is pretty sparse and we have 4 covariates. Looking at the data in the table format was not very informative. This is why I propose to next visualize the data using DATExplore. DATExplore is our application for data visualization. So what I have done here with DATExplore is that I have just loaded the data set and tell to the application how to interpret the different columns of the data set. So, and then a number of plots are generated automatically. So here what I see first is the Tobramycin concentration plotted as a spaghetti plot over time. And I can now start to explore a bit my data. I can, for instance, check the individuals one by one. I can split the data based on the covariates. Here, for example, I split by sex. And in each case, it looks a bit messy because the data is sparse, but I can't do much about it right now. What I can also do is to plot one covariate with respect to another one. So here, for example, I can plot age with respect to the creatinine clearance. And what we see is that there is kind of a strong correlation between age and creatinine clearance. And these are the kind of things that you would like to keep in mind once you will build the covariate model. So this was the data visualization with DATExplore. What we have seen with DATExplore is that we have no striking outliers and that age and creatinine clearance are correlated. Now let's move on to the modeling of this data set. For this, we will use the application Monolix. So here I have open Monolix. Let me start a new project. Okay, so this is how the graphical user interface would look like when you open Monolix the first time. In the part here, we define the data and the model that we want to use. In the part below, we define the initial values for the parameter estimates. At the bottom, we define where we want to save our results. And at the top, what kind of estimation task we want to run. So let's first define the data and the model. So I go here to data, and I browse into my computer up to my data file. And here I need to assign the different columns. Most of them are automatically recognized based on the header, but some are not. So for example, CP, which is my column for the measurement, is not automatically recognized. So I will assign it as Y, which is our keyword for the measurement column. I need to do the same also for the covariate. So weight is a continuous covariate. So I assign it as curve. Same for the age, continuous covariate. Same for the creatinine clearance. And sex is a categorical covariate, so I assign it as cat for categorical covariate. I accept. Next, I need to define my model, both the structural part and the statistical part of it. For the moment, I don't have much information about my data, so we can start with a simple one-compartment model. I can define my model by clicking here on Model File, and I will directly go to the Monolix library, the PK library, and here I have a number of models that I can just pick from the list. So I have a bolus administration. I will choose a one-compartment model parameterized as KV, so the volume and the elimination rate. I accept. Next, I need to define the statistical part of the model. I will start with the residual error model here. I can pick it up from the list. I like to start with combined, which is a constant plus proportional residual error term. As I need to define the individual parameters, here by default, a log normal distribution has been chosen for the volume and for the elimination rate. This is appropriate, so let's keep it like this. Below here, I have the variance-covariance model, matrix, sorry. For the moment, it is diagonal, meaning that I have inter-individual variability, but I will not estimate correlation between parameters. I will keep it like this for the moment, and we will see later on if we need to change. And the part here is for the covariate. We will use it later on too. Now, before running any estimation task, I would like to choose reasonable initial values. For this, I can go here to check the initial fixed effects. I will increase a bit the number of points. So what we see here is for each individual, I have in blue the data and in red the model prediction using the parameter values here. And I can change the parameter values in order to do a rough manual fit. Here it's hard because the data is sparse. So let's, for example, start with these two parameter values here. I click Set as Initial Values, and they are now taken into account here as initial values for the fixed effects. Before I run, I will save my project. So I go to Project Save, and I will save it next to my data set as Project 1, for instance. Okay, so now let's first estimate the population parameters. When I click here, it will launch the SAM algorithm for parameter estimation. And what we see here is how the parameter estimates evolve over the iteration of the algorithm. The algorithm works in two phases. So what you see before the red line is the first phase, where we explore the parameter space a lot. And then we have automatic criteria to detect that we have stabilized, and we switch to a second phase where we really converge to the minimum. If we want to have a look at the estimated parameter values, we can go here to last result, and here I see the estimated parameter values. For the moment, I have a single value without any uncertainty about it. So what I can do next, for instance, is to calculate the Fisher information matrix and to derive the standard errors from the Fisher information matrix. So I click here, it runs, and if I go back to my result file, I now have the parameter, the standard error, and the relative standard error. I can also calculate the individual parameters, either the mode or the mean of the conditional distribution. I will calculate the mode, which is also often called the EBs, the empirical bias estimates. If I click here, calculate, and I will find the result in a result file. So if I go back to my folder where I have saved my project 1 project file, I have a new folder that has been created with the same name. And if I go in it, I have here file indiv parameters, where I have the mode for the volume and the elimination rate for each individual. I can also calculate the log likelihood. If I click here, again, it calculates, and the result is printed at the end of the result file. So here I see the log likelihood, the Kaike and Bayesian information criteria. Now, if I want to diagnose my model, it's good to look at some graphics. By clicking here, I can generate a number of graphics automatically that will help me to diagnose and improve my model. The first graphic is just a spaghetti plot of the data. The next one here are the individual fits. So what I see here is for each individual, in blue, the observation, and in green, the prediction using the individual parameter values. This is very useful to diagnose your structural model, especially when you have dense data. Here we have sparse data, and it's a bit harder to see. I next have the observed versus predicted plot, either using the population prediction or the individual prediction. Here for the moment it looks good. I can choose to plot it on log-log scale to focus a bit more on small concentrations. And here, maybe for small concentration, it seems that I have a deviation. So maybe I could try to use a two-compartment model to capture a bit better these concentrations. So let's keep this in mind. I then have the parameter distribution. So here I see the theoretical distribution, and I can overlay on top of it the histogram of the individual parameters to see if they match. And here it looks pretty good. So no misspecification detected here. The next plot are the standardized random effects plotted as a box plot. So here we should have the blue boxes in line with the pink lines. Here again, it looks pretty good, so no misspecification detected for the random effects. Next, I have the joint random effects. So here I have the random effects for the volume plotted against the random effects for the elimination rate. And the pink line is the trend line, so this would help me to detect if I should consider some correlation between my volume and my elimination rate. Here, not really, the line is pretty flat. So based on these observations, what I could try as a next model is, for instance, a two-compartment model to try to capture a bit better this low concentration. So you see really how we can use the graphics to check our model and improve it step by step. So let's try this. So I will again go back. Wait, before I choose a new model, I will click here on use the last estimates, and the last estimate will be used as initial values for the next run. So now that I have done this, I can go back here to model file and choose a two-compartment model. So I choose bolus two-compartment parameterized with the volume, elimination rate, K12, K21. I accept. because I know that my data is sparse, I will probably not have a lot of information, so I will directly disable the inter-individual variability for K21 and K12. And now let's save this project as a project number 2, for instance, and we can run again. So let me check what I want to run and click run so that I do all steps in a row. So again, here we estimate the population parameters. As you can see, for the volume and the elimination rate, the parameters will not move much because we already had a very good initial estimate. But for K12 and K21, they change a lot and then they stabilize. And when we detect the stabilization, to then move on to the second phase. We calculate the individual parameters as we have done before. The Fisher information matrix and the likelihood. We generate the graphics. And here, if I go back to the ops versus spread, and I go back to the log-log scale, okay, interesting. Here we see that it has improved. I don't have this small deviation anymore. To compare the model, I could also go to the results and compare the log likelihood if I want to, or using the AKK or Bayesian criteria. Here, I mean, you probably don't remember the last value, but I can tell you that the model has improved. We have a lower AKK information criteria. If I go back to the graphics, let's, for instance, now have a look on the covariates. What we see in this plot is on the y-axis the transform parameter, so that the transform parameter is in a Gaussian space, plotted with respect to the covariates. And this helps us to see if there are some correlation between the parameter values and the covariates, and if we should consider a covariate on some parameter values. So for example, if I go to settings, information to display the correlation coefficient, we see here that we have a strong correlation between the elimination rate and the creatinine clearance, also between the elimination rate and age, and maybe also between the volume and the weight. Maybe let's focus on this one first. So first, from a biological point of view, it makes sense to consider the creatinine clearance as a covariate on the elimination rate. So maybe we could consider this as a first covariate to add in our model. And what we also see is that here the relationship between the creatinine clearance and the log of the elimination rate is not linear. It has this banded shape. So what I will do first is to transform the creatinine clearance. So let's do this as a next step. So I go here to transform, and I can take the creatinine clearance, and I defined a new covariate that I will call log of the creatinine clearance. That will be the log of my covariate. And in addition, I will center it using the mean from the data set. I click OK. And I can now add the creatinine clearance as a covariate for the parameter K. If you want to know what is behind these clicks, you can always go to this icon here. And here we display the formula for the parameters. And if you take the exponential of this formula, you would recover the usual formula using the power law for the creatinine clearance. Again, I can use the last estimates and run again. Maybe this time I will focus mainly on the Fisher information matrix and the graphics. I run. So as before, the parameters that I already had in my model don't change much. And the beta parameter corresponding to the covariate will change a lot and then stabilize. So if I go back to my covariate graphic, so I still have this strong correlation between the parameter and the covariate. What I would like to check now is if I have remaining correlation between the random effects and the covariate. So I go to settings and choose to display the random effects. And here what I see is that I have no remaining correlation for the elimination rate and the creatinine clearance, but I have also no remaining correlation between the elimination rate and age. And this makes sense if you remember what we had seen in that explore, that age and creatinine clearance were strongly correlated. So you really see how we can use the graphics to stepwise improve our model. I won't go further in this stepwise model development because it is not the main focus of this webinar. So let me directly show you what I had as a final model. So my final model was looking like this. I have a two-compartment model with a proportional error model. I have inter-individual variability on the volume and the elimination rate, but not for K12, K21. I have the creatinine clearance as a covariate on the elimination rate. Also on, I have also the weight as a covariate on the volume and the elimination rate. So this is a small overview of Monolix. One more thing that I would like to say is that for the moment I have shown you the basic graphics. We have some more graphics that you can see here. So we could have a look at the VPC, at the residuals, and so on. This will be part of a next webinar, maybe, that will be more focused on Monolix. So if I go back to my slides, so we have ended up with a two-compartment model. K12, K21 do not have any inter-individual variability. The elimination rate and V have inter-individual variability. Part of it is explained by the covariates, and part of it is unexplained and is captured through the normal, through the random effect. Here you have again a summary of the population parameter values that have been estimated. So we now have a population PK model that characterizes the pharmacokinetics of Tobramycin. We have parameter estimates, we have inter-individual variability, and part of it is explained by the covariates. Now we would like to use this model for optimal dose finding for specific individuals using Simulix. So we have two main ways to find an optimal dose for a specific individual. Either we can use the covariates of this individual, or we can try to get even more information on this individual by using therapeutic drug monitoring. Therapeutic drug monitoring just means that you give a first dose and you measure the concentration in the blood for this patient at a few time points in order to adapt the next dose. So to do this, we will use Simulix. Simulix is a flexible simulator, and it comes as a function of a R package called MLXR, so we will need to call it through R script. And it is very flexible in the sense that you can either reuse all the information that has been defined in the Monolix project or redefine new elements. So this is true for the model, for the number of subjects, the outputs, the treatments, the population parameters, and the covariates. So here are the steps that we will follow. I will first show you a simple example on how to use Simulix so that we get a bit familiar with it. And then we will ask ourselves, if we use the default treatment for Tobramycin, which is 1 milligram per kilogram every 8 hours, which percentage of the patient will really meet the therapeutic window, so the efficacy and safety targets. Once we have done this, we will move on to a really specific individual. So this individual will have renal impairment, so it will have a constant creatinine clearance of 30 ml per minute and a weight of 78 kilograms. And for this specific individual, we will use the covariate information to try to find a dose and interdose interval that has higher chances to be safe and efficient. And finally, we will assume that we got that this patient got therapeutic drug monitoring, and we will see how we can use this information to adapt the dosing even better. So let me start with my first script. So here I have opened our studio, and this is the R script. And the first thing that I will do is to load the MLXR library. And I also load a second library that just helps me to arrange subplots in graphics. So now that I have loaded the MLXR library, I have access to the Simulix function. And the call to the Simulix function, you can see it here. The main argument of this function is the argument project, where I give the path up to the Monolix project that I have saved. And by doing so, Simulix will be able to recover all the information that have been defined in your Monolix project. So if I run these two lines here, what Simulix will do is that it will use the covariates from the original data set, use the estimated population parameter values from Monolix, take these two pieces of information to draw individual parameter values, do simulation with these individual parameter values using the same dosing and the same output times as in the original data set. All these results are saved in this res1 object that is just a list of tables that contains all the simulation results. And then I can use this object to plot. So if I plot this, what we see here is a simulated data set that is similar but different compared to my original data set. So these are the very basics. Now what we usually would like to do is to start to changing things compared to the original design. So here I have decided to administrate an amount of 80 to all individuals at time 0, 8, and 16. I define this in an object called the AGM for administration. I decide that I will simulate 10 individuals instead of 97. I also define that I would like to output Y, which is a measured concentration, which includes residual error at the following time points. And I will also output CC, which is the predicted concentration without noise between time 0 and time 25 in a very regular manner. And finally, I will use the parameter values, the population parameter values that have been estimated by Monolix, except for the VPOP parameters that are reassigned to a value of 30. Everything I have defined here, I give it in as an argument to the Simulix function, run, and then just plot. So let's do this. So what we see here is the predicted concentration for the 10 individuals and the corresponding noisy measurements. So this was a very small overview of what we can do with Simulix. Now let's move on to our first question. What happens if we administrate the default treatment, 1 milligram per kilogram every 8 hours, to the individuals in the data set? So now what is special is that we have a dose that is per kilogram. So it means that every individual will have a different amount depending on its weight. So to be able to define this, I first need to recover the covariate information, especially the weight, from the data set. This is what I do here. I then define the dose per kilogram, 1, the time at which I want to administrate, every 8 hours, and then I define my administration as a data frame, which just means a table. In this table, I have the ID of the patients, the time of the administration, and the amount is calculated as the dose per kilogram multiplied by the weight for each individual. And then all the rest is similar. I will look at the predicted concentration for 100 individuals resampled from the data set regarding the covariates, and I give all this to my Simulix function and plot. And for the plot, I will use the percentile MLX function from the MLXR package, which enables me to directly plot a concentration prediction interval. So let me run this. And this is what we get And what we see here is that, so the two gray bands are my targets. So in the upper gray band, I should have my Cmax. This is the target for the Cmax. And the lower gray band is the target for the trough concentration. And what I see here is that some people will meet these two targets, but a lot of people won't. We can quantify this a bit better, so I can use my output tables to calculate the Cmax, the Ctrough, and calculate which percentage meets the target. And we see that for 18% of the population, the default treatment will be toxic, and for 87% of the population, the default treatment will not be effective. So this really calls for an individualization of the treatment based on the patient characteristics. So this is what we will do next. So we will consider a person, a very specific person. This person will have renal impairment. So its creatinine clearance will be 30 ml per minute, and its weight will be 78 kilograms. Given this covariate information, I have an idea of the individual parameter values, but I still have some uncertainty about these individual parameter values, and this is captured here as a random effect. So what we're going to do is to do it in 4 steps. I will first consider a typical individual with this weight and this creatinine clearance, so it means that I will set the random effects to 0. I will then simulate the default dosing for this typical individual. If I see that the default dosing is not appropriate, I will write a small optimization script to find a better dosing. And finally, I will put back the random effects in order to check what are the chances to meet the efficacy and toxicity criteria given the uncertainty in the individual parameter values. So I go back to my R script. So the structure is again very similar, except that this time, instead of reading the covariates from the dataset, I define them myself using the known weight and creatinine clearance. I disable the random effects. I define the default treatment, and I run. So let's check what we have here. So if I give the default treatment to this individual, which is a typical individual with this weight and this creatinine clearance, this is what we get. And as you can see, the Cmax is a bit too high, and the Ctrough is really too high. And this makes complete sense. I mean, we know that this patient has a low creatinine clearance, so it has a low clearance for Tobramycin 2. So it means that it is not eliminating very well, and that's why the Ctrough is high. So probably what we want to do with this patient is to increase the interdose interval to give more time to the drug concentration to go down. What I propose to do now is to write a small script to try to estimate how much we should increase the interdose interval to meet the toxicity and efficacy criteria. So I have written here a very basic optimization script that calculates the Cmax and Ctrough. If the Cmax is too high, the dose will be a bit decreased. If the Cmax is too low, the dose will be a bit increased. And if the Ctrough is too high, the interdose interval will be a bit increased. And then I loop and progressively adapt the dose and interdose interval. So I will run this small piece of script, focus here on the graphics so that you can see how the dose and the corresponding concentration prediction evolves over the iteration of the algorithm. So you see I have highlighted the Cmax and Ctrough in green and red, depending if they are in the target or not. And we finally end up with a proposed dose of 1.58 milligram per kilogram and an interdose interval of 26 hours. So of course, the interdose interval of 26 hours is not really feasible in the clinical practice. So I can either choose to use 24 hours instead, or if I want, I could improve my optimization script and take into account these clinical practice constraints, for instance. So now what I see here is a prediction using a typical individual with this with the weight 78 and the creatinine clearance 30. What I will do next is to put back the random effects in order to check what would be the uncertainty on the predicted concentration if I take into account the uncertainty in the individual parameter values. So this is what I do next here. And I will plot it as a prediction interval for the concentration directly. It's kind of a lot of simulation, so that's why it takes a few seconds to run. Okay, so what we see here now is the predicted concentration interval based on the optimized treatment, given the uncertainty in the individual parameter values. And you see it's already better than what we had with the default treatment. I can calculate what are the chances to be safe and efficient. So my chances to be safe are 93%, and my chances to be effective are 77%. So if I go back to the slides and compare to the default treatment, we really have improved the chances to be effective and safe with now the optimized treatment compared to the default treatment. So this is already a nice first step. Now let's assume that we have given a first dose to this individual and that we have monitored its drug concentration at a few time points over time. This additional experimental information, we can use it to get a better estimate of the individual parameter values. So what I can do is that I can compute the probability of the individual parameter that I now have called phi because it is a joint distribution. So I can calculate the probability of the individual parameters phi given the population parameters, the covariates, and the individual data coming from the therapeutic drug monitoring. So this is a joint conditional distribution, and what one usually do is to take the mode, so the most probable value of this conditional distribution, and to consider this as the individual parameters. So let me show you how to calculate these individual parameters. For this, I will go back to Monolix. And here I have the same model as I have obtained from the clinical dataset, except that this time I have fixed the population parameter values here. This is why they are pink, because they are fixed. I have already estimated them before, so now I fix them. I don't estimate them again. And for the dataset, I have changed it, so I have removed the clinical dataset, and I have replaced it by the therapeutic drug monitoring for this individual. Here I have two individuals, but let's focus on the first one. I have given him this dose, and I have measured the following concentrations. So now what I can do is, given the covariates in the data set, the measurements in the data set, and the fixed population parameter values, I can click on to estimate the individual parameters, and I will get them back in my data file. So let me browse here. So this is what I would get. So for my individual of interest, I have the mode for the volume, the elimination rate, and so on. So I can use now these individual parameter values to optimize my treatment again. So let's go back. No, sorry. So now I have one single value for my individual. But remember that I told you, in fact, we have a joint conditional distribution. So if I want to know the uncertainty of the parameter values for this individual, I should get samples from the joint conditional distribution. There is a way to do this in Monolix. It's a small trick. So what I have done is that I went to Settings, Population Parameters, and here I have increased the number of chains, which means that we replicate the dataset to artificially create patients. And then in the graphics, you can go to the covariates graphic. And what you see here are samples from the joint conditional distribution. So what we would like is to get these parameter values to a file. And for this, we can go to graphics, export graphics data, and all these samples from the joint conditional distribution will be saved to a file, and we can use them later on for simulations, for instance. So now that we have these individual parameter values estimated by Monolix, let's go back to R. So I have a fourth script here. Again, the structure is always the same, except that this time we directly work with individual parameter values. These are the mode of the joint conditional distribution. And I will first do a simulation in which I reuse the treatment that has been optimized using the covariates only. Let's check that if this was a good treatment or not. If I run this, we see that the trough concentration is in the target, but the Cmax is a bit too low. So again, we can use the same optimization script to increase a bit the dose in order to have the Cmax in the target. Oops, sorry. So it was supposed, let me close this and run it again. I had a breakpoint in my code, and this is why we could not see it pretty well. Okay, now this is what we are supposed to see. So we start from this concentration here. We just increase a bit the dose, and already at the next iteration of the algorithm, we meet the target. So our new proposed dose is 1.8 milligram per kilogram every 26 hours. Now I would like, as before, to know what are the chances to meet indeed the efficacy and safety criteria given the uncertainty in the parameters. So instead of using just the mode of the conditional distribution, I will use the samples from the joint conditional distribution that I get from my graphics data outputted by Monolix. I run this. And here are the results with the optimized treatment. And we see that we now have 100% chances to be safe and 82% chances to be effective. So if with the treatment optimized using the individual parameters from the therapeutic drug monitoring data, I have improved even more the chances to be safe and effective compared to the previous proposed treatment. So if we look at a summarizing view of it, let's first assume that I have no information at all about my individual, not even the covariates. Then the uncertainty about the individual parameter values are as large as the variability within the population. And this is what you would see here in the beige color for the parameter K. And if I have a huge uncertainty about my parameter, this results in a huge uncertainty for the concentration, and this is why you see here the prediction interval for the Tobramycin concentration is very large in beige color. Now, if I have the covariate information for this individual, then the uncertainty about the parameter value is reduced. I have here a more narrow parameter distribution, and this results in a narrow predicted concentration interval. And finally, if I use therapeutic drug monitoring to gain more information about the individual parameters for this individual, I have an even more narrow parameter distribution and a narrow predicted concentration interval. And the narrower the predicted concentration interval is, the easier it is to find a dosing and interdose interval that meets the safety and efficacy criteria. Now, all what I have shown right now, you can redo it by yourself. All the scripts are available online, so you can download them and adapt them to your needs. what we at LixOft can do in addition is to build up some graphical user interface to have something easier to use. So let me show this to you. Yep, it's here. So here is a small application that we have that you can open directly in a browser. And this is really something that a clinician can use, for instance. So what I have here is that the clinician can give in the dose that he has administered, the weight of the patient, and the creatinine clearance, and the measurements that he has done for the tobramycin concentration, so the time and the measured concentration. And then if I click here, get recommendation, I run in the background the same kind of script as I had in R, and I will get a result directly in the interface, making it very easy to use. So here we recommend to use a dose of 1.54 milligram per kilogram every 10 hours, and the associated toxicity risk is 1%, and the effectiveness probability is 58%. So these are things that we can put in place. We are definitely interested in developing application in this direction. So if you have concrete example and you are interested in a collaboration, don't hesitate to get in touch. And with this, I would like to conclude. So we have developed a population PK model for the tobramycin molecule, and we have used this model to get a priori an optimal dosing regimen for the safety and efficacy criteria. We can do this either using the covariates or the individual parameters obtained from therapeutic drug monitoring. As you could see, the MonolixSuite allows to do this in a very efficient modeling and simulation workflow. All the case study is available online, including all the R scripts and so on. So if you want to download them and either redo it or adapt it, you're welcome. And if you want to contact me, my email is geraldine.eral@lixoft.com. Thank you for your attention, and we now have 10 minutes time for questions. So you are welcome to ask your questions through the Q&A section of the WebEx interface, and I will answer to them orally. Okay, so we have a first question. Why did I use the log of the creatinine clearance as a covariate? So I did this because we could see so let me share my screen again. So if I go back to the covariate figure, and I go back to the settings where I look at the individual parameters, here we see, so here it's interesting, we see both. We see the log of the creatinine clearance and the creatinine clearance untransformed. And you see that here the relationship seems to be not so linear, while if we transform the creatinine clearance, it looks more linear. So this is why I have transformed the creatinine clearance first, is so that I have a linear relationship between the transformed covariate and my transformed parameter. So this is a bit unusual at the beginning, but in Monolix, we always work with transformed parameters, and we add covariates linearly to the transformed parameter. So if I go back here to the expression for the parameter, so it may look unusual in this way because it's all log transformed, but if you take the exponential of this formula, you will exactly recover the formula that I had on the slide with the power law. So we just transform the covariates so that we are able to recover the usual formula, and because we see in the graphics that it is more appropriate. So I have a question about other possible models with Simulix. So now I have shown an example where I have used models from the Monolix PK library, but you are welcome to develop models yourself using the MLX language. So we have a dedicated language where you can, in a very intuitive way, describe models. Usually you can do so via an ODE system, for instance. And then you can describe any kind of models, including models with metabolites or any kind of complex models. So regarding the trick that I have done in Monolix to get samples from the joint parameter distribution, so we use a Monte Carlo procedure, and this permits us to draw samples from the conditional joint distribution. By default, we have only one individual, and then we get at the end one draw from the sample from the joint conditional distribution. And just one draw is not very useful, and that's why we kind of replicate the data set to create a lot of artificial individuals, and then we get at the end one sample from the joint conditional distribution per chain, per replicated individual. And in this way, we can get a lot of samples of this joint conditional distribution. They do not appear in a specific output file. They appear in the graphics, and this is why we need to export the graphics data to recover them. So in this version of Monolix, it's not super, I mean, it's feasible, not super convenient. We are working so that in the next release, it will be easier to do. So I have a question about the steady state behavior of the concentration after one or several doses. So in all my simulations, I have considered a lot of doses, and I look at the concentration after, I think it's 30 doses. So I'm sure that I am in steady state. This is something that you can choose. You can choose to work and to look at the concentration after the first dose or after a lot of doses to be at steady state. This is as you prefer and as is relevant for your own case. I then have a question about the different methods to estimate the Fisher information matrix in Monolix. So let me share my screen again. So here for the Fisher information matrix, we have two options. We can either linearize the system and then calculate the Fisher information matrix, or use a stochastic approximation, which does not require to linearize a system. So you can do both. Usually using the linearization is faster and a bit less precise, and using the stochastic approximation takes more time but is more precise. Here, because we had a limited amount of time, I have used linearization, but you could also use stochastic approximation, and in this case the results are very similar with one or the other one. So when I consider, when I calculate the individual parameters using the mode, which would be equivalent to the EB's empirical bias estimate, I use the model that is defined in the Monolix interface, and so it's not exactly the one that has been published in the literature. It is the one that I have currently in my Monolix interface. And the residual variability is the one that I have in the interface, so it's the one that I have estimated just before during the population parameter estimation task. I have a question about the difference between mode and mean when calculating the individual parameters. So let me again show you my screen and the Monolix interface. So here, when I calculate the individual parameters, I can choose either the mode or the mean. So you really need to remember that we have a conditional distribution for the individual parameters, and it is a distribution. And from this distribution, you would like to have one representative value. And you can either choose to choose the mode, to calculate the mode of this distribution, which would mean the most probable individual parameter value, or you can choose to use the mean of this distribution, which permits to a bit better grasp if the distribution is really skewed, for instance. And this is really a personal choice. Both are relevant. They have a bit different meanings. So then it depends what you really want to look at. I have a personal preference for the mode because it means that it is the most probable value, and this makes sense when you want to look at the individual parameters and the resulting prediction for the concentration. Okay, I see no more questions, so thanks a lot for your attention and have a good day.